This homework problem is coming up, and it has what I call this tripod. It's got a frame with a force applied to it. This particular question asks us to determine the magnitude of the moment of the force about the base BC. So with the force being applied at point D, what kind of rotation does that cause around the edge BC? So I've created a Onshape file that can help demonstrate some pretty key pieces of information about this great tripod problem. So first, it may look like an equal-sided tripod, but pay special attention to the projection of V down to the XY plane. And we can see that better in Onshape. Um, all right, from this top view, with my X and Y axes turned on, right, we can see that it's not an symmetric tripod, right? We have an idea of the points A, B, and C, and here's the force applied up at the top. All right. So if I want to investigate, what does it mean for a moment based on a force? So the first thing I'd like to take a look at is I'm going to look at the moment about A. So this force applied at point D, what kind of rotation does it cause around point A? And here's how I've shown this. Let's look normal to this sketch. We're looking at it in 2D. I have a line drawn representing the force. Okay. Forces are not in inches or millimeters, but I have established the line length based on what the overall magnitude of the force would be. I used Onshape to physically create this vector in 3D space. So going from point D, I traveled backwards the X, the Y, and the Z locations. So this length here represents my force in relative scale. Now, when we have a moment about a point, that is created with a perpendicular distance, force times perpendicular distance. So this is a force in 3D, right? This vector here, um, well, it goes from this point up to this point, and then we have some changes in X, Y, and Z to get there. So distance from A to the force, the perpendicular distance, right? This plane was created through the points A and D. Actually, it was created through the point A and D, and then also the end of the force. So it's a plane that includes the force and it includes point A. So now if I look normal to this force, right, perpendicular to the force, this line here represents the perpendicular distance from the point to the 3D force. And I can draw this circle as representing the motion of this force around that point A. Right? And essentially, if I have a force times a distance, I can represent that as a length. Again, it's not actually a length, but here's my force rotation around point A. If I take a quick look at the rotation around point B, right, it's much smaller. That the perpendicular distance from the force to point B is much lower. So this diameter, this visualization of the moment, view normal to that one. So the rotation around point B is going to be significantly less than the rotation around point A because of that shorter perpendicular distance. All right. So now that I've got this kind of visualization of how much rotation the force causes around the point, I can extrude that and show that as a vector. Okay. So this moment vector is perpendicular to the plane that contains the position vector and the force vector. right? So the position vector and the force vector live in the same plane. Perpendicular to that plane, I have the axis of revolution, right? And this has a length relative to the diameter. If I were to show the same length on B, it would be shorter, and I'll show you that, right? The same length on B is shorter because it has that smaller tendency to rotate. Now, the other part of the question isn't just what is the moment about A, right? So this is showing my axis and my moment about A, but also what is the moment about an axis, not a point, but about an axis. So here is my moment about AC, right? And in this image, let's view normal to this image. Um, here. So this plane includes the moment and the axis, normal too. Let's move this around a little bit. All right, so this plane isn't necessarily just a horizontal plane, but it's the plane that contains both the moment and the AC axis. So if I want to know how much of this moment is projected onto the axis AC, what we do is we draw a perpendicular, right? I mean, that's generally what we're doing. We're projecting perpendicular that moment onto the axis. So how much does that moment tend to cause rotation around this axis? And we can measure it off this edge. So here's a really cool part though. Moment about C, right, is also on that same edge. And there's the moment about C. It's at a different angle, it's got a different magnitude. Right? But if I take that same moment about C, let me make that visible, and I project that onto AC, here's a plane that contains both AC and the moment about C, and I project it onto the edge AC, right? Now these look like different lines, but the length of this line, the projection of the moment about A onto AC, is the same length as the projection of the moment about C onto AC. So I hope I can represent a few things with this um, in-depth CAD model, and that's how to visualize the planes, right? The plane that contains the force and the perpendicular distance, how the moment axis is perpendicular to that plane, how the same force causes different rotations around different points. And then finally, how we can use those planes. They're not horizontal and vertical necessarily, but we can include planes to show projections of moments onto edges and how this force at the top causes a rotation around AC. We can calculate that out with the moment about C or with the moment about A, and we'll still get the same tendency to rotate around that axis.